is base is 2. Okay, there is no translations at the moment. It's not adding on a certain number. It's not moving left, right, up or down. The only thing we have is a naught, which is what you're multiplying to the 2. This is a dilation of factor a naught from the x-axis. Okay. Now, in an application sense, the reason why we put a naught is because that's the amount that you're starting off with. So it was 5,000 and you times it by 2, you're doubling it. So it was 5,000 times 2, it's double, depending on what the power is. If it's 2 to the power 2, then it's now quadruple. Yeah? Normal value times 4 will make it quadruple of that value. So hence a naught, though we say it is the dilation factor, it is actually the starting point as well. So in an application problem, they will tell you that a population starts off blah. So they say it starts off at 5,000, and then after 2 years, it is now 10,000. That's how we're going to model it. We're going to say it's an exponential growth, and we know that the initial and final. Yeah, our job is to find out K and time. Sometimes, well, they told us 2 years or 3 years. That's what we know. We don't know what K is though. Okay. Same thing over here. It could be a decay. A naught here represents again what you start off with. So it might start off at 10,000, and after 3 years, it is now 4,000. Okay, so it's dropped down a certain amount. So this is the final. That's the initial. That's the base. In our case, radioactive decay or cell growth will have a base 2. What we don't know is K. Your job usually is to find K and then find the values. Okay, that's generally what we're doing. But the terminologies that you need to get used to, I want you to copy this one down. For cell growth, the letter K represents generation time. Okay, what is generation time? It's kind of like, well, yes, even if the cells grow, right, let's say it doubles itself, but then how many does it double per second? Is it like, does it triple it, like, does it double itself 3 times per second, 4 times per second, 5 times per second? That's what generation time describes. So T could be per second. 1 second, I might have 3 of them. Okay, so if 1 second I split up into 3, then we've got 3 per second, so it's a third each second. Okay, so we call that K the generation time, and I'll do an example so you can see. Whereas the other K doesn't have a name, it's just decay, it's a constant that it drops. Okay, so that's why I wanted you to copy these two. If it's decay, it makes sense that you have a negative in the power. If it's growth, there is no negative, it just keeps growing. That's why it's constant, but you just need to know that K value. Okay? Most of the time, the problems that you may deal with is either one of those two, or you'll have just your normal A naught times, and you don't know what the base is, and it could be just KT. Usually. Okay, that's the general solution one there. So that's usually what you would get. They'll tell you what you start off with. They might tell you that you're tripling rather than doubling, and they will tell you how long it takes to get a final amount, and your job is to find K. Okay? But specifically in your problems there, you may either get radioactive decay or you may get cell growth. So just remember, there's only 2 scenarios there. One's dropping and one's increasing. Cool? Let's have a read of this one. It says here, what is the generation time of a bacterial population that increases? So there's a key word there. It says increases from 5,000 to 100,000 cells in 4 hours of growth. Okay, so in this case here, out of the 2 formulas, which one am I doing? Is it the cell growth or is it the decay? Cell growth. Okay, so it has to be cell growth because I know it's increasing, and our job here is to find the generation time, which is what I mentioned just then. Generation time is K. So this is my formula. What do I have? What's the 5,000 represent in this case here? A naught. This is your A naught. That's how much you start off with. You start off 5,000. And we don't know actually we do know the base is 2. So we know B is 2 because it's a cell growth problem. We know A naught is 5,000. Okay, start off 5,000 and it's doubling itself or cell growthing up until a certain point. After certain number of hours, 4 hours, it is 100,000. So the final product, you got 100,000, but that only occurs after 4 hours. Now what is equal to 4? T. T is the time. In this case, it's t equals in 4 hours. It's in the time in hours. Now, most of these problems or your formulas is you'll normally calculate it in minutes, not in hours. So just a note, just probably go back to your own notes there. This t represents minutes. Okay, we usually do it in minutes, not hours. So that means in this particular problem, unless it was talking for hours, in our problem here, we have to convert it all to minutes. Okay, so let's have a look. 4 hours. In 4 hours, we want to convert that to minutes. So we know t equals to 4 hours, but 4 hours, how many minutes is that? Good, 4 times 60, 240 minutes. Okay, now let's put it all together. So I've got A naught. We're gonna, oops, sorry. I'm just gonna do it by hand here. We've got 100,000 is equal to A naught, which is 5,000 times 2 to the power of, instead of 4, it is now 240 minutes divided by k. And now you've got yourself an exponential equation, and your job is to use what you've learned from 13D, 13E to solve the problem. You can use a CAS at this point as well because it's applications, but I want you to learn both algebra and CAS. Okay? So let's solve this. How do I solve for k? I need to get rid of the 5,000. That's times 5,000, so I would not log 2. I need to do something with the 5,000 first. Divide. Okay, so you can't normally log 2, but remember that 5,000 is a problem. You want to just get 2 by itself. So before you log, get rid of 5,000. So divide both sides by 5,000, which is 20. How many 5,000 is 100,000? Or it's the same thing as saying how many 5s in 100? Got 20. 20 is equal to 2 to the power of 240 minutes. Okay, now you want to get rid of that base 2. The inverse of base 2, which is log base 2. So log base 2 on both sides. Log base 2 of 20 is equal to, now if you do log base 2, they cancel out. So you're left with 240 over k. Okay, so now I've actually got log 2 of 20 is equal to 240 over k. How do I solve for k? Remember, if you don't like fractions, what do? What have I taught you? Multiply it. See, it's divide k, then opposite of dividing k is times k. So if I times k to both sides, I'm going to write in red so you can see, green. Times k, times k. Now I know the k's will cancel out. I got 240. This is k times log base 2 of 20. And right there, how do I get rid of times log base 2 of 20? Divide, because opposite of times is divide. So if I divide both sides now, divide both sides by log 2 of 20, k is equal to 240 divided by log 2 of 20. Whatever that answer is as a decimal, which I'm going to use my calculator. If you guys have a calc, start getting it out because we're going to be using it quite a bit for today. There's clear history. It was, what was it again? It was 240 divided by log base 2 of 20. Is that right? 55.53. So this is 55.53. Okay, but what does that mean? What's the K mean?
5 times.
Yeah, it's the generation time. So that's how long it takes to generate itself. Okay, so that's your generation time. Okay, and that's in minutes because we calculated minutes before. Okay. Any questions so far? Did that feel all right? So it's just more, is it growth or is it decay? Let's try next one. If it's growth or decay, it's going to be 2. Yeah. The only time it changes is if they tell you something else. So they might say that the cell is growing triple its rate. So then it's not double anymore. Yeah. So it will be 3. So they'll tell you. I'll find an example later, and you can see when it changes. Okay. Let's try this one. So if you have growth or decay, it's always going to be 2. B is always going to be 2. Okay. Let's have a look at this problem. Same idea. After 1,000 years, so you got time now. 1,000 years, a sample of radium-226, sample of whatever it is, okay? Sample of something has decayed to 64.7% of its original mass. Okay? Now this is going to be key 64.7% of its original mass. The problem is we don't know its original mass. Okay? Find the half-life of the product. Anyone know what half-life means?
The amount of time it takes for it to decay to half of its original.
Very good. That's for those who haven't learnt it from physics or chem. Half-life just basically means, I'm going to do it in blue. Half-life is just saying how long before it decays to 50% of its original amount or size or mass, okay? So in our case here, we know that it's dropped down to 64.7% after 1,000 years, but we want to know how long it takes to drop down to half of its size. Okay, so let's, in this case here, we have to first determine, is it a growth or is it a decay problem? It's a decay, because I started off at 100%, which is the original, and I'm slowly dropping, this is decay, down to 64.7 after 1,000 years. So, we know it's a decay problem. What's the formula for decay? I'm just going to write it here. There's your decay problem, but we know the base has to be 2, because it's a decay or a growth problem, and they haven't told us whether the base changes or not, so we assume it's 2. Okay? Now, I got B, which is 2. I don't know what K is. I do know T, that after 1,000 years, okay, my final amount, because it says after 1,000 years, my final amount is how much? Good, 64.7% of its original mass. Now the problem is I don't know the original, so it means I don't know what A naught is. Let's call A naught X. Okay, so if it's, I'll use a different letter actually. Let's call it, instead of X, let's call it Q. Okay? So I don't know what Q is. I don't know the original mass, but I know the final is 64.7% of Q. So that's what you're going to write down, because it really literally just said we don't know what the original mass is, but it's 64.7% of the original mass. Another way of writing that is 64.7% is the same thing as saying 0.647. Of means times Q. So another way of thinking about it is 0.647 Q is how much the final amount is. Does that make sense what I'm doing? Okay, so I'm going to rewrite it. A is now 0.647 Q. Whereas Q is Q. Q is the original amount. I don't know how much that is. Okay? So if we write it all out as an equation, I've got 0.647 Q is equal to Q times 2 to the power of K, I don't know, negative K, but I also know it's 1,000. See my equation there? What I want to find out is K. But I also have a problem with the Q. Okay. But it just so happens this problem is nice. Lucy? Only for generation time. Yeah, so for the generation time, we because it's cells, we don't calculate in hours, we calculate in minutes. But in decay time, especially in this one, this is talking about years, so we normally calculate in years for this one. So it's very weird, isn't it? In year 12, it's better questioning, better sort of layout, but for the year 11, they're trying to really fit in a couple of this must be case, which is not true. It doesn't always have to be in time or in minutes, and if it is, it will tell you. So in year 12, the questions are better performed because they'll tell you what T represents, and they'll tell you what A represents and whatnot. So you're right, it's hard to tell in this particular case, but in the textbook, in this example, they're taking it as years. They're taking T as years. It's weird. Yeah. All right, here we go. So we've got K and Q we don't know, but the nice thing is that Q is being times to both sides. And what I can see already, because that's times Q, if I divide this side by Q and the right-hand side by Q, I'm also going to divide the left-hand side by Q, which cancels out. And that's nice. So if I divide both sides by Q, which ends up being 0.647 is equal to 2 to the power of negative K times 1,000. Now that's just nice, because now I can find out K. Well, why did I need to find out K? Because my goal is to find a half-life. Now I can't find a half-life until I fill out all the unknowns. Okay, I still don't know what K is. So I need to find K first, then I can work out the half-life. Okay, so let's go with this one. From here, how do I solve if I have 0.647 equals to 2 to the power of negative 1,000 K? I need to find K, so I need to remove the base 2. What do you do? Log. Log base 2. That's the inverse of exponential. So logging base 2, log base 2 of 0.647 on the left, log base 2 on the right cancels out, and you're left with negative 1,000 times K. So therefore K, to find out K by itself, divide both sides by negative 1,000. Type this in your calculator. That will tell you what K is. Okay, so what I've done is from this step, I said to get rid of 2, log base 2 on both sides. Log base 2 of 0.647. I've still got negative 1,000 times K. To get K by itself, I divide both sides by negative 1,000. Okay, so dividing this by 1,000. K equals to log 0.647 divided by 1,000. There's a negative there. Okay? I wrote it as a fraction just so it looks a bit nicer, that's all. Okay? Now, on our calc, hopefully, understanding up to this step, I'm just going to show you all the steps here. We get up to this step, K equals 2, negative 1 over 1,000 times log 2 of 0.647. If you do that in your calculator, you should get 0.0000628. Okay, now I've got K, but I still haven't solved for the question. Oh, sorry, I'll go back. So after getting K, I still haven't got half-life. How do I find half-life? You said half-life is 50% of the original. True? That's what you said. You said half-life. So what do we want? We want half-life. What is half-life equal to? You said 50% of the original. So another way of writing that, which I'll do it in blue here, 50% is 0.5 of Q. That's what you want. So you want to know what half-life equals to. So half-life equals to 0.5 Q. The question is, how long does it take to get there? Okay, so now we sub it in because we know that A, the half-life, we want to know when, how long before you have 0.5 Q. What you guys just did was you did 0.647 of Q. Well, instead of doing 0.647, let's do 0.5. It's the same idea. So here, I would say I want it to be half-life, half of the original. So half of the original, if this is Q, that's Q, then I can say, I'll just take a step back here so that you don't get confused. This is what we want. We want to know what half-life is equal to. This one we already have. That's the formula over here. So I'll write it out. It's A naught times 2 to the power of negative K times T, which is 1,000. A naught, which we called Q, is equal to half of Q. And you can see already, if you divide both sides by Q, Q's cancel out. You end up with 2 to the power of negative 1,000 K. Oh, sorry, not 1,000. We didn't know what the time was. We're trying to find time. So negative T times K is equal to half. And then from here, we can now solve. That's a base 2, it's an exponential. That's a half we did in exercise 13D. Change a half to a base 2. So instead of writing half, we can write it as 2 to the power of negative 1. Since the bases are the same, powers have to be the same. If powers are the same, you now solve for T, because you already got K. You already know K was 0.00628. Are we following here? How does that feel? Yes, no? No. All right. I'm just gonna finish off this part here. I'm just gonna go back, take it back a step. Here we go. Things that we didn't know. We only had this. We know B is 2, negative KT. I don't know what K is. A naught, I called it Q. A, which we know was 64.7% of Q. So I wrote 6.647 Q. I found that dividing Q on both sides will cancel out and I get 0.647 equals 2 to the power of negative KT. I use log rules to remove it all to find K because I already know what T is. So I use log rules and I get log base 2.647 is equal to negative K times T. But you already know what T is. T was 1,000. So here we solve for K and K was equal to log base 2 of 0.647 of a negative 1,000 because we already know T is 1,000. So you got K. But that wasn't our goal. Our goal was to find half-life. How long does it take to get to half-life? That was our goal. How long does it take to get half of the original amount? So that's what I wrote. If A equals half-life, which is half of the original amount, I want to find how long. So I substituted this A here. That's what I did. So when I sub that in, it's half Q, half, if you prefer decimals, I'll use decimals here, 0.5 Q is equal to A naught, which we don't know, which is Q, times 2 to the power of negative K times T. Our job was to find how long. We already got K in decimals, I worked it out before. We already got K, so we're just trying to find T. Just so happens if you divide both sides by Q, log base 2, divided by negative K, you get your answer. Okay, so just think about the process of what you're doing. You're trying to find an unknown. Once you got the unknown, your job was to find half of the original. Okay, so that's what I did in the next slide. I got up to this step, and I said, that's your A value. I substituted half A naught into this equation. I cancelled out the A naughts because I divide both sides. I changed the base. Instead of writing half, to power negative 1. Exercise 13D, if bases are the same, powers are the same. So if powers are the same, negative KT has to equal to negative 1. T must then equal to negative 1 divided by negative K. Two negatives cancel out, but I already got K. See, K was here. We already figured out K. Sub K in, 1 divided by K gives me 1,591.95. That's the number of years that it takes so that it reduces down to half of the original. Because that's what I want. I said I want that to be half the original. That's original, half, 0.5. Whereas the other one was 0.647. So instead of 0.647, you're still doing the same things, it's just that I didn't know K. So now that I know K, I can figure it out for 0.5. Does that make sense? Yeah, so your goal is to find half-life, which is 0.5 of the original. And it just so happens that the half-lives, the originals will always cancel out. Okay? All right. So that was an example of growth, and then we've done an example of decay. Now, you have this problem, which is meant to be easier. This is more like the year 12 kind of problems, okay? In year 12, they will give you an equation. Listening? In year 12, they give you an equation. They give you a restriction, and they will give you coordinates. So you look at this, they say the points 1, 6, and 596 lie on this curve. We don't know what A and we don't know what B is, right? But we do have an X and a Y coordinate. We have X and a Y coordinate. You got 2 coordinates, 2 unknowns. Means it's possible to solve. Here, they say find the values of A and B if you already know A is bigger than 0, meaning positive, and B is bigger than 0, means B has to be positive as well. So, in this case here, this is my equation. They told me y equals to a times b to the power of x. They gave me a coordinate. 1, 6. So when x is 1, apparently y is 6. So that's what I did. I sub 1 in, I sub 6 in. I've got myself an equation. That's one equation. I sub in the second one. They said when x is 5, y is 96, so I did the same thing. 96, 5. Now because this is an application problem, you can use your CAS. You can use your CAS to define, solve, which is what I've been teaching since term 1. I wanted you guys to define and solve. Now if you did it on your CAS, this is what it looks like. And I'll show you how to do it as well, just in case you've forgotten. I defined the function, so I did f of x equals to a times b to the power of x. I did solve. Now the benefit of defining it is then you can rewrite it like this. F of 1 equals 6 means when x is 1, y is 6. When x is 5, y is 96. Instead of typing the whole equation again, I've just typed it in its notation, said find a and b. They figured out a and b. Okay, but right here I've got a equals -3, b equals -2, or a equals 3 and b equals 2. Now which one of those is correct? Because they already told us. A had to be a positive number, b had to be a positive number. Therefore the answer has to be a equals 3, b equals 2. Now, whilst I am pushing for for you to use your CAS more, because that's where I think our class can improve on, and I'll show you how to do that again, I still am big on the algebra, on how to do this manually. Does anyone know how to solve when you have 6 equals to a times b, and you have 96 is equal to a times b to the power of 5? How do I solve this? There's substitution method, and there's a quicker way, which I like, the elimination method, but you can't add or subtract in this case here. See, elimination, we're used to adding and subtracting. Yeah, it's absolutely fine that if you can add, subtract, and you can multiply, divide. That's as simple as it is. So in our case here, I can see that the a's and the a's are the same. So if I said take second equation divided by the first equation, a divided by a is going to cancel out. And that's what I want. I want to eliminate. That's the point of elimination, is to eliminate one of the variables. So here, if I called this equation 1 and equation 2, then 1 divide equation 2 will give me a divided by a, 96 over 6, times with b5 divided by b. Now this is nice. A divided by a cancels out to be 1. b5 divided by b, which is b to the power of 4. And 96 divided by 6, let's see, does that even work? Yes, it does. That is 116. Okay? And then to find b is equal to the 4th root of 16. Now some of us may find that difficult, or you can use your fingers and trying to calculate something times itself 4 times, or use what you learnt in 13C. 4th root of 16 is the same thing as saying to the power of a quarter. Okay, so I'll write here 4th root of 16 is the same thing as saying 16 to the power of a quarter. You can do a factor tree, break down the 16 to 2 to the power of 4 times a quarter, and then you can write 2 to the power of 4 times a quarter, which ends up being 2. Okay, so if b is equal to 2, you have either 2 or -2 as one of your answers, but we know that b has to be positive 2. Because when you're 4th rooting, remember it's like square rooting. You get plus and a minus answer. Okay? Yep, substitution will work as well. If you just rearrange it to write like 6 over b equals a, and then substitute this into that, that would work as well. Okay? But I'm just showing you that as the problems get more difficult, elimination method where you can divide works as well. There's nothing wrong with that. Okay? All right, now for those who didn't know how to use their CAS, I'm going to show you what I did. I'm going to clear all. Yep, that's what I want to teach. So we all know how to define, so I'm going to quickly define on my calc. Define. So in case you forgot again, it's menu actions define. F bracket x equals to, it was a times b to the power of x. Make sure to put the time symbol in between. Otherwise, the calculator doesn't know it's separate. Okay? Press enter, decide to find it. Now, how did I get those two equations? So I can type in solve. So menu 3, 1. Okay, you type in solve in your catalog. So next to the common functions, next to the 9 and next to the book, this is your commons tab. In your tab, there are all these functions here, and out of them all, I want to use this one, braces with 2 functions. That's what I did. Okay, so in there, I typed in when x is 1, the coordinates was 6. Yeah, so from the question, they told me when x is 1, y is 6. So that's what I'm saying. If I sub 1 into the equation, f of 1, which is the y value, y equals 6. Okay, and I'll do the same for the next one. F of 5 equals to 96. So those are my 2 coordinates. I've defined the function already. I want you to solve for comma A, comma B. Okay? Because that's you got 2 unknowns. As long as you have 2 equations, then they can solve it. You've got 2 unknowns, 2 equations, you've got an x and a y coordinates already. You can solve for A and B. Okay? And then you press enter. That's how you get it. Okay? So I'm just going to move the mouse away. I do want you to practice that, practicing solving on your CAS, sketching on your CAS. Now, I also found another cool thing. For those who didn't know, I'll show you this cool thing that I just learned. If you do control page, add a graph for me, okay? Let's type in, let's do a function. What's something that we've learned so far? Let's do square root of x plus 4. I'll put a negative in there. So negative, and I'll do translate up by, actually it's negative, translate by 5, okay? That's my graph. Whoops. Okay? Now, you know how some of you asked me, how do you find the y-intercept? And I said that the best way is to do it in your CAS. I found a really cool thing. Apparently, you can go menu. Instead of what I taught you, I said, for those who did ask, I said, go geometry, go to points on line, and then put a point on the graph, and then change the coordinates. Don't do that. It's a quicker way now. Go to trace, graph trace. Okay, so if you go to menu, again, trace, graph trace. What graph trace does is, if you move your cursor left and right, okay, it will find all the special coordinates, right? But if you happen to have a really big graph, pressing left takes too long, yeah? It's really hard to find all your coordinates. So what you should do now, once you're in this mode, press 2. I'll press 0, because x equals 0 is when you have a y-intercept. So you press 0, it comes up as x equals 0 in the box there. Press enter, and it'll tell you the coordinates. So that means if the question asks you what is the y value when x is 7, you can do it here too. You can say 7, press enter, and it tells you what. It tells you this is where when x is 7, y is 1.68. And that's a nice way to do it. So graph trace, we used to just press the cursor button and press left, right, and it tries to move. Graph trace is good to find your maximum minimums if you happen to be close. You move close to it, it will tell you the maximum minimums. But this is a nice and quick way to find coordinates in your y-intercepts if you want to use them. Okay, so you type in the number that you want, press enter, but you can only choose for x, which means if you want to find your y-intercept, let x equal 0, and we'll find out the y values. Okay, so those are just a nice little trick with your graph trace if you want to find y-intercepts on your CAS. For those, again, some questions will ask to round to 3 or 4 decimal places. Notice mine is only 1.68. A short way of changing that to more decimal places, if you didn't know, whoops. How do I do it again? I was going to show you, let me put a point, and I'll show you. I'm just going to put a point onto this graph. You know how I've currently got 2 decimal places there? If you want to make it longer, move your mouse or cursor to the decimal that you want and press plus. Press the plus button. So if you put the press button, so if you move it right here. Oh wait, I'm going to do it over here. There you go. If you press the plus button, it opens up for you and it tells you more digits if you needed more. If you put a minus button next to it, then it reduces it. So if you press minus, it reduces, plus, 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 plus increases so that you can get the answers if it's asking for 2 decimal places. So my year 12s normally lose a mark because they don't round it to 3 or 4 decimal places, and it does matter. Yeah, so it does matter what the question asks. So make sure to read the question right. If you're graphing it, make sure you're putting in the correct decimal places. Okay? All right, other than that, that is exercise 13H. Tomorrow's lesson I'll do a revision, and I may talk a bit about inverses, but really what you need is D, E, G, and then H. Okay, D, E, G is your outcome number 1, SAC 1, SAC 2, H, applications. Okay. Or if you can do D, then AB is already there. Yeah, so you're going to be able to sketch exponentials, solve exponentials, sketch logs, solve logs, and then applications. So 5 skills. 5 skills. There we go. I'm going to leave you guys there. Either practice those questions there or catch up wherever you're up to.